Hello, and welcome to this edition of the 2023 Von Karman series. My name is Nikki Weirick from JPL's Office of Communications and Education, and welcome to a discussion on the upcoming solar eclipses, the annular in October of 2023 and the total in April of 2024. Both of these eclipses are crossing over most of the continental United States, which is a rare occurrence. We'll discuss the science behind eclipses and how to experience them, even if you can't be there in person. A reminder to our audience, it is not safe to look directly at the sun, and special eye protection is required for viewing any type of solar eclipse. And also, as always, if we run into any technical difficulties or small failures, we ask for your patience, and please do stick with us. We'll get them sorted out as soon as we can. Joining us for this wonderful discussion this evening as our questions co-host is JPL Public Engagement Specialist Rachel Zimmerman Brockman, who has worked on several missions and projects at JPL, including Cassini at Saturn, 2 astrobiology projects, and a citizen science project called Exoplanet Watch. Rachel also works with the Office of Technology Transfer, the Radioisotope Power Systems Project, and the Solar System Ambassadors. Hiya, Rachel. Thanks for joining us this evening.
Hi, Nikki. Thanks so much for having me here tonight. I want everybody to remember this is your space program. We want you to be involved in this conversation. So if you're watching on YouTube, X, Facebook Live, or LinkedIn, ask questions in the chat box. And our social media team will bring in as many questions as we can to get into our talk tonight. If you don't see the chat box, reload your page and it should be right there.
Awesome. Thank you so much, Rachel. We're so glad to have you. Also joining us this evening is Jason Craig, data visualization developer, producer, and technical manager at JPL. Jason joined the Solar System Visualization team in 2005 and created CGI animations for missions such as MER, MRO, Juno, Mars Odyssey, Cassini, Curiosity, NISAR, and many others. In 2015, he became the producer and technical manager of NASA Eyes software, which has won multiple Webby Awards, received NASA Software of the Year Award, and was a part of both the Emmy Award-winning teams for Cassini and InSight mission events. Hi, Jason. How are you this evening?
Hi, Nikki. I'm good. Thank you.
Jason, we're glad you're here, and we'll touch base with you a little bit later. We're even going to get to see more of NASA Eyes as well. But now let's meet our first speaker of the evening, Dr. Marin Anderson, research scientist, astrophysicist, and radio astronomer at JPL. She studies the time-varying phenomena in our universe at radio frequencies, from explosive extragalactic events to radio bursts from nearby stars and exoplanets. She is a scientist with the Gabbard program and is also the project scientist for long wavelength radio telescopes at Caltech's Owens Valley Radio Observatory. Hi, Marin.
Hey there, Nikki. I was just safely viewing the sun behind me here with my eclipse glasses.
Oh, what a great example you are setting for everyone this evening. So, Marin, tell us, what is an eclipse?
Yeah, so an eclipse is just a generic term for when one astronomical body passes in front of another one. And if we go to slide 1, or slide 2 rather, we'll see a really cool image of an eclipse. But we see eclipses all the time in the solar system and out in space. For example, the rovers on Mars see eclipses when the moon Phobos of Mars passes in front of the sun. And astronomers see eclipses all the time when they're looking in other stellar systems, other solar systems, when they see the transit of an exoplanet in front of its host star, and they use that transit to infer the presence of that exoplanet. What we're seeing in slide 2 here is actually an eclipse in our own solar system. This is an image of Cassini, taken by Cassini, of Saturn. Saturn's eclipsing the sun here, and we can't see the sun because Saturn's blocking it, but we do see is the presence of the sun behind Saturn due to the nice illumination of Saturn's atmosphere, and also the backlit rings of Saturn. There we go, that's that image. So yeah, eclipses happen all the time in the universe. Fun fact, Nikki, you're actually in this photo. If we zoom in a little bit, there we go. Nikki, you're in this photo. Everyone out there watching, you're in this photo too. We're all in this photo. If you look just above and to the left of the main rings of Saturn, you'll see a blue speck there, and that's not actually dust on your screen. That's Earth.
Awesome. So it's good to know we're in this picture, a tiny little blue dot back there. But tell us, what is a solar eclipse compared to, say, just eclipse the title?
Yeah, so in my unbiased opinion, a solar eclipse is the coolest kind of eclipse. And if we go to the next slide here, we'll see an animation of what you expect to see when you see a solar eclipse. But I like to call solar eclipses that happen on Earth sort of a cosmic coincidence. And I say that because I like alliteration, but also there's something really special about solar eclipses as viewed from Earth. So the moon of Earth is about 400 times smaller. The diameter of the moon is about 400 times smaller than the sun. But the sun happens to be about 400 times further away than the moon from Earth. And so thanks to geometry, the effect of that is that during a solar eclipse, when the moon passes between the Earth and the sun, what you get is the moon completely covering the disk of the sun. They happen to be the almost exact same angular size in the sky because of that distance and size discrepancy. And so what you get is a total solar eclipse, where the moon completely obscures the disk of the sun. And in addition to being able to experience nighttime in what would normally be daylight hours, if you're in the path of totality, you can also see the faint atmosphere of the sun, which we call the corona, which is Latin for crown. It's a really beautiful event that's really unique to our Earth, Sun, Moon system. And another cool fact is that it's a cosmic coincidence not only in space, but also in time. So when the moon originally formed, it was much closer to the Earth. So for many billions of years, a solar eclipse as seen from the Earth would have been much less impressive. The moon would have completely blocked out the sun. It would have been much larger in angular size than the solar disk, and we wouldn't have been able to see this beautiful faint atmosphere called the corona around the sun. And it's unique because take advantage of your ability to see a solar eclipse now. So the moon's actually drifting further away from the Earth in time at a rate of about 1.5 inches per year, which I always see is online is listed as, the rate that your nails grow. So the moon's drifting further away. So about just over 500 million years from now, a total solar eclipse won't ever happen. There will only ever be something called an annular eclipse, where the moon won't fully obscure the disk of the sun, and you'll still be able to see a ring of the sun's disk around the moon. So get it while it's hot.
Exactly. And in fact, not only is it rare and unique for us to experience this, but also there's 2 upcoming eclipses. So can you tell us, how are the 2 upcoming eclipses different?
Yeah. So if we can hop to slide 4, I can explain a little bit about the geometry of what's happening during an eclipse. So what we're seeing here is just a diagram of the Earth, the Sun, and the Moon, and not to scale. And what's happening during an eclipse is in the phase of the new moon. So when the moon is between the Earth and the Sun, it just so happens to pass in front of the Sun, and it creates 2 kinds of shadows on the surface of the Earth. The first shadow that I'll talk about is the umbra, the inner shadow. And if you're a fan of Latin, umbra is Latin for shadow. And that's the part of the shadow where the moon is completely obscuring the sun. The penumbra, which is just outside the umbra, penumbra being partial shadow in Latin, is where the moon is casting a shadow, but it's not completely obscuring the face of the sun. So if you were in the path of the penumbra, but not the umbra, you would see a partial solar eclipse. The moon would pass in front of the sun, but what you would see was this sun turn into kind of a crescent shape during the eclipse. If we go to slide 6, I can talk about specifically what happens during an annular eclipse. So I lied a little bit when I was talking about the moon completely covering the sun. Well, a lie of omission. So the moon doesn't always perfectly cover the disk of the sun now, not just 500 million years from now when it's too far away. And that's just because the moon's orbit is not perfectly circular. It's actually a little bit squished, or elliptical as we call it. And so that means sometimes it's further away from the Earth and sometimes it's closer to the Earth. So when it happens to pass into that new moon phase and get in line with the sun and the Earth and create an eclipse, if it's in the part of its orbit, which we call the apogee, where it's furthest from the Earth, then it won't completely obscure the disk of the sun. And you'll get something called an annular eclipse. Annular eclipses are still really cool, and we have one coming up on October 14th of this year, which is, I think, 22 days from now. So I encourage everyone to view the sun during this time. And the effect that you get when you view an annular eclipse, if you're in the path of annularity, is this really beautiful, what we call ring of fire effect around the moon, where you can see the outline of the sun that's not being obscured by the moon. And it's quite beautiful.
That's amazing to see. And just a reminder for everyone, when we talk about viewing the eclipse, we want to make sure you're wearing your safety glasses and taking safety precautions. So yes, we do want you to view it, but we want to make sure you are safe doing it. Now, we've talked a little bit about both of these eclipses, but what kind of an experience is an eclipse for people?
Yeah, so if we could hop to slide 8, viewing an eclipse is really a multi-sensory experience. Usually eclipses are framed in terms of what you see, and we've been talking about what you see in eclipse today. And indeed, it's really beautiful. But there's so much more that happens, especially when you're in the path of totality. If there's a total solar eclipse happening, the moon is completely obscuring the disk of the sun. There are so many senses that you can use to experience a total solar eclipse. So in addition to seeing the corona, that faint atmosphere around the sun, the kinds of things you can expect to experience are temperature drops. So because you're essentially experiencing nighttime, you can expect temperatures like what you would experience at nighttime. So the temperature can drop by as much as 20 degrees Fahrenheit during totality, so you'll feel cold. Because of that temperature differential between where you are in darkness, in essentially nighttime, and places on the Earth outside of that path of totality, outside of that umbra shadow, because of that temperature differential, you'll get a pressure differential, and that can generate a breeze. So you'll feel a wind. Depending on where you are, animals or insects will also think it's suddenly nighttime in the middle of the day. So animals that normally get ready for bed at nighttime might start chirping for birds. Insects, grasshoppers might start chirping. On the other hand, it could become really eerily silent as creatures, wherever you're located, if you're in the path of totality, start to experience what they think is nighttime. So it's really a truly, I think, surreal experience that a lot of people have said have moved them to tears even. So yeah, a really unparalleled experience.
Wow. I mean, I can't wait for these eclipses to come personally because I will be so excited. But so is the audience. They're asking a ton of questions. So I want to throw it over to Rachel. Rachel, what are they asking out there for Marin?
Sure. One of the questions that we got in is from Brian on YouTube, who's asking, what is your suggestion for forecasting the cloud cover for being able to see these events? Because eclipses don't look very good if it's cloudy.
Yes, Brian from YouTube, that is an excellent question. Yes, one of the most important things if you are planning to view the eclipse from the path of totality is to consider what the weather will be like at any given location. I don't have the ability to forecast the weather, unfortunately. So check forecasts, check typical weather conditions at given locations in the eclipse totality path to see where you can maximize your chances of being able to view the solar eclipse. Because if there is cloud cover, obviously you won't be able to see the corona. You will be able to still experience all those cool things I talked about in terms of what you'll feel when it essentially becomes nighttime during the day, but you won't be able to see the corona. So checking the weather is important. Also, planning where you go in the path of totality is important. So the closer you are to the center of that totality path line, the longer the eclipse will last. It's not going to last any longer than 7 minutes, so it's a very ephemeral thing. But you can go from seeing it only for on the order of a minute to maximizing your time to up to 7 minutes. So thinking about where you are in the path of totality in terms of weather and how long you want to be able to view totality are both two really important things.
Let's see. James on Facebook is asking, how often do we see total solar eclipses?
Yeah, that's a great question. So I lied again in my explanation of the moon's orbit. Well, again, not a lie of omission. So the moon's orbit, we already talked about how it's not perfectly circular. It's actually a little bit elliptical. The other important thing is that the moon's orbit is not in the same plane as the Earth-Sun line. It's actually slightly tilted or inclined, as we call it. That inclination is only 5 degrees, so it's very slight. But that 5 degrees is enough to make it so that most of the time we don't get a solar eclipse. You might imagine that if the moon's orbit wasn't inclined at all, if it had a 0-degree tilt to it, if it was in the plane of the Earth-Sun line, that every month we'd get a total solar eclipse with every phase of the new moon. But we don't, and that's because of that tilt. And you can think of it as like the moon passing either above or below the sun, depending on where it is in its orbit or where the tilt is in the orbit at a given point in time when it reaches the new moon. So it turns out we only get a total solar eclipse on Earth on average about every 18 months. And any given geographic location on Earth will only ever see a total solar eclipse on average every 375 years. So if you live somewhere near or in the path of totality for the solar eclipse that's coming in April of 2024, you should really take advantage of it because it's a really special event.
Do we have time for one more question at this point, Nikki?
Yeah, Rachel, let's do one more before we move on.
One more. Okay, so Anna on YouTube is asking, how do we predict when and where eclipses will occur?
Oh, wow, Anna, that's a really cool question. So if you'll allow me to step back in time 2,000 years while I answer your question. So the Babylonians actually were able to predict solar eclipses. They figured out by observing enough solar eclipses happening and lunar eclipses, they figured out that eclipses actually repeated every 18 years-ish, 18 years and 11 days, and some more precision that I can't remember. And they did that just by observing. So they didn't have the ability to predict where an eclipse would happen, but they knew approximately what year and day, and approximately even what time an eclipse would happen somewhere on Earth. And that 18-year, 11-day-ish cycle is called the Saros cycle. So now if we fast forward to the early 1700s, an astronomer named Sir Edmund Halley actually rediscovered the Saros cycles. So he rediscovered what the Babylonians had learned 2,000 years prior, that eclipses repeat on this 18-year cycle. But he did them one better. He was able to actually predict the location of the eclipses on the Earth. And he did so accurately. He predicted there would be an eclipse through London, I believe, in 1712 maybe. And he did that using a very new theory of gravity at the time, which was Newton's theory of gravity. So he used a really precise locations of the moon in its orbit relative to the Earth and the sun, in combination with his theory of gravity, to be able to predict that an eclipse would happen in London and that it would happen at this specific time in this specific geographic area. So nowadays, we have even better theories of gravity than what Newton was dealing with back in the 1700s. So we can compute really precisely where the moon and the sun and Earth will be relative to each other out in time. And we can do it now with really high accuracy. So we can predict totality to within seconds, and we can predict eclipses hundreds of years out into the future with a precision of about minutes.
That's incredible to think how we can predict those things, and how I appreciate you taking us back in time there, Marin. We're going to come back for some more questions in just a little bit, but I'd love to pull up image 9. And Marin, I'd love to have you tell us what we're looking at here in image 9.
Yeah, so this is actually a really great segue from talking about Newton's theory of gravity. So an eclipse in 1919 was actually used to verify a new and improved theory of gravity, courtesy of Einstein. It was used to prove the theory of general relativity, or at least give one more evidence that the theory was right in this instance. So in 1919, Sir Arthur Eddington, another British astronomer, went out to view a solar eclipse, and his aim was to observe the apparent offset in the positions of background stars during the eclipse. So Einstein's theory of general relativity was basically that what we perceive as the force of gravity is actually a deformation in space-time. So you can kind of think of it like someone sitting in the middle of a trampoline, and space-time is the surface of the trampoline, and their mass is deforming that space-time. And so what Einstein predicted was that because of this general theory of relativity, because of the way the sun deformed space-time due to its mass, due to its gravity, that the light coming from background stars would appear to deflect around the sun. And that's what I'm showing in this image. So the solid star at the bottom is the actual location of the background star, which astronomers at the time would have known. They would have mapped the locations of these stars. And then the dashed star above it is the apparent position of that star during the solar eclipse, due to the way that the mass of the sun deformed space-time and curved the path of the light coming from that background star. So if we go back to our trampoline analogy, it'd be kind of like if you were trying to roll a marble past someone sitting in the middle of the trampoline. You can imagine if you rolled it really far away from them at the edge of the trampoline, it would travel in a straight line. But if you rolled it really close to them, it would kind of deform around them. The path of the marble would be altered due to the mass of that person. So that's what Einstein predicted with general relativity, and he was proven correct with Sir Arthur Eddington's observations of the apparent offsets of stars during the 1919 eclipse. And this kind of observation was only possible during the eclipse because in order to see the background stars, it required that the bright surface of the sun be covered by the moon. So during a total solar eclipse, when the surface of the sun is covered, you can start to see background stars, just like you can at night. And that's what enabled Arthur Eddington to make this observation and to prove Einstein correct in at least this part of general relativity.
Marin, there's some great science we can do today using eclipses. So tell us a little bit about what kind of science we do with eclipses.
Yeah, so with eclipses, we're not trying to prove GR anymore. We have much more extreme astrophysical environments that we can use to do that, like around supermassive black holes that are millions, billions of times heavier than our sun. But the kinds of science that we can do during eclipses today are much more relevant to the sun itself. So if we can go to slide 10 here, there's a really nice image of this corona that we can see. Again, that's Latin for crown. It's the faint atmosphere surrounding the sun. The center of the image is actually a photo taken from space of the surface of the sun. I believe it was taken at X-rays. The outer part of the image in red was also taken from space using something called a coronagraph, which kind of does the same thing that the moon does during an eclipse. It blocks out the light from the disk of the sun. But coronagraphs have to cover a much larger area. So you only see the very outer reaches of the corona, as you can tell from this image. In order to see the inner parts of the corona much closer to the surface, where a lot of the structure, a lot of the exciting stuff is happening, you really have to view this part from the ground during a total solar eclipse. When the moon is just perfectly covering the photosphere, or the surface of the sun, it reveals all of this beautiful structure in the corona.
And you've got another image of the corona for us as well. So if we can pull up the next image, and you can tell us what this one is as well. Just beautiful.
Yeah, so I love this image. So this is a 3-color image, again, of the corona. The moon is blocking out the photosphere, this disk of the sun. The white parts of the corona in this image is just a white total intensity color image of the corona. The red parts of this image correspond to a particular iron line. Iron is present in the corona, and it gets heated to extremely high temperatures, and it turns out that this red color that you're seeing in this image is mapping iron that's at temperatures of almost 2 million degrees Kelvin. And the green parts of this image are also iron lines in a slightly different state that are at an even hotter temperature, double the temperature of the red line, so almost 4 million degrees Kelvin. And this beautiful image, in addition to being really striking, is revealing a lot of structure in the corona. You can see loops, you can see regions of magnetic structure. And this part of the sun is really exciting because it's really where all of the activity happens from the sun, in particular the magnetic activity. So the sun has an 11-year magnetic activity cycle. So it goes from a period of a lot of magnetic activity to a period of almost very few magnetic events and very low magnetic activity, and then back to a period of high magnetic activity every 11 years. And the corona changes during this time. Although actually what the scientists that took this image found, they were, I think you could call them eclipse chasers. So they observed the sun from as many eclipses as possible over a time period longer than that 11-year magnetic activity cycle. And what they found is that the corona, in particular, the corona that's at that cooler 2 million degree Kelvin temperature, is actually quite stable over the course of that 11-year magnetic activity cycle. And that's important because that part of the corona is really what drives something called the solar wind. You can think of it as like a breeze of subatomic particles that come off of the corona of the sun and interact with everything in the solar system, including Earth. And so it's really important that we study the solar wind and other kinds of magnetic activity driven events that happen in the corona of the sun, because they can have huge implications for life on Earth.
And there are ways for this science to be done that involves the community too. So let's talk about one of those. You're involved with the Gavert project. You want to tell us about that?
Yes, yeah. If we can go to the next slide. Gavert is a project that's really close to my heart. It's a really unique partnership between JPL and the Lewis Center for Educational Research, which is based out of Southern California. And they operate the Goldstone Apple Valley Radio Telescope, which is what Gavert stands for. It's a retired DSN antenna that gets used to conduct science with K through 12 students, with citizen scientists across the world, allowing people to do radio astronomy science anywhere in the world. So you get to operate the telescope itself. And there on the left is Miss Nancy, my colleague, who's our Gavert operator. In addition to operating the telescope, you actually get to do real science with the data. So it's a really exciting project. And it covers science ranging from observing Jupiter and its radiation belts to monitoring supermassive black holes to looking for technosignatures out in the galaxy from potentially other civilizations. But the project that I'm most excited about is something called Solar Patrol. And we have a program to observe the eclipses with the Gabbard radio telescope. And if we go to the next slide, I can explain a little bit about what's so exciting about observing the eclipse at radio wavelengths. So if we can play this movie while I talk, a big limitation of radio telescopes is often the angular resolution of those telescopes. So the angular resolution of the Gabbard antenna is represented by that black circle there. And it's quite big relative to the disk of the sun. And the reason radio telescopes have such poor angular resolution is just because the angular resolution is related to the wavelength of light that you're observing. And since radio telescopes are observing such long wavelengths of light, they have quite poor angular resolution. So what we want to do during the eclipse is take advantage of the moon passing in front of the sun to kind of get some angular resolution for free. So the moon will pass in front of what we call the beam of the telescope, the part of the sun where the telescope is looking, which is usually at something called an active region, which is a region in the corona where very exciting magnetic activity is happening, usually above sunspots that you can see on the photosphere. And what happens when the moon's disk passes in front of that black beam is we suddenly get significantly better angular resolution that corresponds to the edge of the moon passing in front of features in the active region. So suddenly we have angular resolution that's orders of magnitude better than what we could get from normal observations. And what we're seeing in this plot is the flux we observe, or the amount of light we observe from that active region as a function of time. And you can see that as the moon's edge passes over that circle, we get less and less light from that region as the moon covers it. And then as the moon moves away again, we get more and more energy. So we can use this to kind of get angular resolution for free out of the moon.
Excellent. It's amazing what we can do using something that's already happening to do all of this science with it. So I want you to tell our audience, where can the eclipse be viewed?
Yes, yeah. So if we go to slide, let's see, 16B, I think it is, there's a really nice map of the total solar eclipse. Actually, can we go one more slide? Yeah, there we go. So this is a really nice map that you can find online that tells you almost all the information you need to know about where to be if you want to view the annular eclipse in October of 2023, which is represented by that line cutting from Oregon down through Texas. And then where you want to be if you want to view the total solar eclipse, that's that line going down or going up from Mexico up through the Northeast. So what these black paths show you is the path of annularity for the annular eclipse and the path of totality for the total solar eclipse. If you look really closely, you'll also see circles that represent the shape of the umbra or the moon's shadow. And you'll also see times that represent when totality will start at those geographic locations. And there's also lines that tell you how long totality will last at a given part of that path. So those are all key bits of information that you need to know if you're planning your trip to view the eclipse. There's also lines that show you what the sun will look like if you're not in the path of totality. So essentially what fraction of the sun will be covered and essentially what it will look like in a partial eclipse.
Great. So now that we know where to view it, Rachel, I want to bring you back in to tell us a little bit about how to safely view the eclipse. And on the bottom of the screen right now, you should be seeing a link you can check out for more safety tips, solarsystem.nasa.gov/eclipses/safety. So Rachel, tell us, how can we view this safely?
Yeah. Well, if we go to slide 17, you'll be able to see people wearing eclipse glasses to watch an eclipse. So very much like the glasses I'm holding up now, they're completely blacked out. You can't see anything through them. And you'd almost think that you can't see anything at all. The only thing you can see through eclipse glasses is the sun. And if you have eclipse glasses that somebody gave you or that you've bought somewhere, and they are from, let's say, the 2017 eclipse. You watch the 2017 eclipse, you want to come back and use these glasses to look at the new eclipses in 2023, 2024. How do you know if it's safe to use those glasses? Make sure they're not punctured, scratched, bent, anything that would let any light through them at all. There's also a safety standard. They're written right on the glasses. The current safety standard is 12312-2. That is the current ISO safety standard for glasses. So if you're buying glasses online, make sure they have that level of safety standard. Anything else is not guaranteed to be effective. There are some libraries that will be handing out glasses. Not all libraries will be handing out glasses. So check with your library ahead of time to find out if they know whether they're getting glasses. Solar system ambassadors will be getting glasses, and if they're in your community, you can arrange for a meeting with them, and they can perhaps share some glasses with you. If you're using a telescope, do not look through a telescope unless the telescope has a solar filter on it, and the solar filter doesn't have any holes in it or scratches on it. So the only way to safely look at the sun through a telescope during an eclipse is if it has the solar filter on it. Sunglasses are not eclipse glasses. Just because it blocked a little bit of the sunlight doesn't mean it's safe to watch an eclipse. It has to block all of the light except the sun itself. So only eclipse glasses that are designed for solar viewing are acceptable for watching the eclipse safely. There are other ways you can watch an eclipse if you don't have eclipse glasses. If we go to slide 18, you can see that you can build your own pinhole camera. And basically you take a cereal box or a shoebox and some aluminum foil, and you put a little pin in the aluminum foil, and you can actually look through the hole in the box, and you can see a projection, a shadow of the eclipse as it's happening. You can do something even simpler. You can take a colander outside and you can look at the shadow. Don't look at the sun, but look at the shadow and look at the shapes of the holes in the colander that are projected through the holes. And you'll actually see a mini version of the eclipse in each of the holes from the colander. You can also do something as simple as taking a hole punch to an index card and putting a hole in the index card and holding that out and then looking down at the shadow. Again, not up at the sun, down at the shadow. So that's another safe way of looking at eclipses. You can also experience eclipses in other ways. Marin was talking about how there's a temperature drop, so you can do some temperature calculations before, during, and after the eclipse. Slide 19, we have eclipse soundscapes, where you can actually hear the changes in what's going on around you during the eclipse. So you can hear crickets chirping during the day. You can hear animals and birds behaving differently. There's also, NASA is producing a Braille book. So you can feel with your fingers, both in Braille, and there's also raised pictures of the kind of what's happening during an eclipse with the moon blocking the sun. So you can feel the eclipse that way with getting a feel for eclipses. I think they said they're making a 2023-24 version of that book. The one that's on the screen right now is from the 2017 eclipse. We're getting a lot of questions about, like, where do you have to go to see the eclipse? Is it only in one place? So we're talking about that path of totality that's in slide 15 and 16, talking about like where you'd need to be to see annularity or to see totality. One other quick question that we want to address is that people are asking the difference between a solar eclipse and a lunar eclipse. So Marin, maybe if you could very quickly talk about that.
Yeah, so a lunar eclipse is when the Earth passes between the moon and the sun, and so it casts a shadow on the moon. And lunar eclipses are a lot more commonly viewed from Earth, and that's just because the Earth is so much bigger than the sun in the sky from the perspective of the moon. So we talked before about how solar eclipses are such an amazing cosmic coincidence because the moon happens to be just exactly almost the same angular size as the sun in the sky as viewed from Earth. But the case is much different for the moon. The Earth has a huge angular size relative to the sun. So it blocks out all of the light from the sun, and it casts a huge shadow. So you can see a lunar eclipse, if it's happening, from anywhere on the night side of Earth at that time. In contrast, a solar eclipse, you'll only be able to see in a narrow swath, and you'll only be able to see totality in an even narrower swath that's usually on the order of like 100 miles wide. And that swath travels in a particular path across the surface of the Earth. It's different every time, although it does repeat on that 18-year Saros cycle. But that's what those eclipse maps are showing you. They're showing you where to go to see totality, that entire black band stretching across Mexico all the way up to the Northeast, for instance, during the total solar eclipse in April of 2024. That's showing you where you need to be, anywhere in that path to view totality.
And actually, this is a great moment for us to bring Jason in. So before we open up for any more questions, Jason, I would love for you to show our audience an amazing way to experience the annular eclipse using NASA eyes. So tell us a little bit about NASA eyes, your experience with eclipses, and what we can see. And folks, there is going to be a link down at the bottom of the page for you. It's eyes.nasa.gov. So Jason, take it away.
Thank you, Nikki. I would love to do that. So if you go to eyes.nasa.gov, as Nikki just said, we have a free 3D simulator. In fact, we simulate the entire solar system, and you can see every eclipse for 100 years, from 1950 to 2050. So pick your eclipse, you can see the 3D simulation of it. So on screen, if you go to eyes.nasa.gov, it's just a browser-based simulation. So all you need is the internet and a web browser on any phone, any device, Linux, Mac, Windows, what have you. And we are democratizing what's going on with NASA. We also have 150 plus missions simulated in this software. So if you could put the URL on the bottom of the screen, I'm going to show you Eyes on the Solar System, which is at the top. You just click on that little banner and it'll take you here. I'm going to maximize the screen. This is just in a web browser. This is just in normal Google Chrome browser. So right away, you can tilt and pan and zoom and move out, and anything with a label, you can click on it. On the left, I have some bookmarks for all the cool stuff coming up with NASA, because there's so much that NASA does. This software is an attempt to show you visually what is going on. So right there on the left, I have a nice 2023 Annular Solar Eclipse link. So you just click on it like I'm doing here, and in you go. So this is going to give you a little extra information about the eclipse. This is Earth. This is the actual time coming up at October 14th. You can see down here. And even better, you can control space and time. So I'm going to fast forward and rewind as I see fit. We've got a little slider down here, so you can move that. So right there, you can see the shadow. We've made a little fake purple shadow cone so that you can see where it passes. And if you zoom in, this is the annular eclipse. The annular, it's not going to be 100% blackout, as Marin was saying. So right here around the middle, you're going to get about 85% or so. On the left, I have controls for you. So this is the main one. And if I scroll down, I can turn off this shadow cone, that purple shadow cone. And I can also turn off the contour map. And then if I go back and forth, you'll just see the shadow passing. But I'm going to turn the shadow back on so you can see where it is. I'm just going to rewind. There it is, down in South America. We're going back. We're going back, and you can see the shadow passing over North America. So I'm going to stop time right there. I'm going to we have lighting settings here as well, so be sure to use natural lighting so you can see it properly. And I'm going to zoom out so you can see kind of the cosmic dance going on. You see that purple shadow. It hasn't quite hit the Earth yet. And there you go, Sun, Earth, Moon. And you can see it's about to hit. So that shadow cone will be going through North America. And let me go ahead and do that. I'm going to turn on the contour maps again. It's just an easy on-off click over here. And so you can kind of plot your trip. If you can't see the eclipse, I highly recommend going to see this one or the total eclipse in April. And you can kind of plot out where you need to go, and you can simulate it here. So it happens, reasonably quickly, as Marin was saying, 7 minutes max. I chased the 2017 total solar eclipse all the way into Missouri. I was planning on the Kansas City area, but it was cloudy. So don't get discouraged if it's cloudy, but check those weather reports and chase it. Chase it, because it's well worth it. So I drove halfway into Missouri to catch that one. So there you see the shadows moving out. I also have several views over here. So if you want to go from the moon's perspective, just click this behind the moon. And there we are. You can see the moon casting the purple cone towards Earth, and you can always move around and see the sun back there. We are very, very lucky to have that coincidence of the angular size matching the sun from our distance. So do take advantage of it. So again, you can always just fast forward and rewind, see what you want to see, or go to the next view. I'm going to show you the Earth-Moon view. So as Marin was saying, it's not just that the orbit is not a perfect circle, it's that it's tilted 5 degrees. So if I fast forward here, you can see the shadow cone is going to miss most of the time. So I'm going 3 days per second, and you can see where that kind of purple shadow is going. And it's going to miss the next time around. So it's 5 degrees off, so it's not always going to hit. So when it does, it's kind of fun to see it. Now I'm going to go to the sun, earth, moon all in a row view. So you can also see the same dynamics at work. And I'll just fast forward there. You can see the shadow nowhere near. And actually, if I just fast forward here, we'll get to April, and you'll see it's dead on. So again, you can simulate 100 years in here. You can go to any eclipse you want. In fact, I'm going to jump over to the total eclipse. So here we are. I'm going to maximize the screen here. I've jumped ahead to April 8th, 2024, and now we have the total. I don't have the fancy stuff in there because we want people to check out the annular one, but soon we'll have the feature for this as well. But you can just fast forward to the eclipse and watch this stuff happen. So I'm going to rewind here. Now you can see the shadow is different than the annular one. See, it's going to cross up through Texas and head on up north. So I'm going to go just a little faster here. And this is natural. So if you just play with the software, you'll see this all the time. And it's not just Earth. You can also go to other planets as well. So let me show you an example of that. So here's Jupiter, and this is pretty nifty. This is a triple eclipse. So you can see 3 little shadows on Jupiter. Now, Jupiter is massive. It is the monster of the solar system. But if I pull back, you can see at this particular moment on January 23rd, 2015, there are 3 little eclipses. You've got Callisto, Europa, and Io. They're all casting a shadow. And what's fun is if I fast forward, you can see it start to go away. You'll see this one on the right smear and go away. There it goes. And then the next one will go. This one's farther away, so it's a little hazier. And then you see this nice bright one there. So you'll see this if you just like go to Jupiter or Saturn, you're going to see this just naturally from time to time, because there's eclipses happening all over. It's really cool. It's just like something's getting in your light. Something is blocking your light, and it can be just small, like Jupiter's moons. Again, I want to make sure you know that if you just click on any label, in you go. So there's Io casting its shadow. Also, with eyes on the solar system, you can see upcoming events as well, like the Psyche launch and OSIRIS-REx sample return capsule coming up this Sunday. So I would encourage you to play around with eyes, go find any eclipse you want, and check out any mission you want to see. So I'm going to go back to the home page. If you have a favorite mission, by all means, just go here. We have 147 spacecraft to choose from. So yes, on the left, again, check out the Annular Eclipse feature. And by all means, go explore around eyes and see what you want to see. We try to simulate it all so that you know what's happening, because NASA does so much cool stuff. There's always something interesting to see. And even working here, you never know everything that's going on. So please check it out. And thanks very much.
Yeah, thank you, Jason. And you didn't know this, but Gigi on YouTube, her 8-year-old niece, was asking if you could see eclipses on other places in our solar system. So you already answered that. Thank you, Gigi's niece, for that great question. So now we want to open it up to all of you asking questions. We only have a few minutes left, unfortunately. But Rachel, let's start with a couple of questions. What are they asking out there for Marin and Jason?
Sure. The Blackbird on YouTube asks, how long does a solar eclipse last? And could one last long enough that it gets dark enough to see the stars, or at least the bright stars and planets?
Yes, yeah, that's a great question. And the answer is yes, yeah. So totality can last, as I mentioned before, as long as 7 minutes. It can last as short as a minute. So it's important to try to find a place in the path of totality as close to the center of that line as possible if you want to maximize your ability to experience totality. But yes, it gets as dark as essentially twilight. It will get dark enough that you'll be able to see stars in the sky. And depending on the geography and topography of where you're viewing the eclipse from, you'll experience a 360-degree sunset, basically, which is due to the fact that you'll be able to see regions that are outside of that path of totality, outside of the umbra shadow and the penumbra that are slightly lit up by the partial eclipse there. So you'll have this beautiful ring of sunset around you, but in the sky above you, you'll be seeing stars, and you'll be seeing that beautiful corona that I described, that gas that surrounds the sun, plasma, I should say, that's millions of degrees Kelvin, and is probably, if you are able to view it, the hottest thing that you will ever see.
So Julie on Facebook asks, is there any time during an annular eclipse when it's safe to look at the sun without your glasses?
Oh, that's such a good question. The answer is no. Never view the annular eclipse without your eclipse glasses on. Never look directly at the sun ever. And you can never look at it directly during an annular eclipse. You can look directly at the sun only during a total solar eclipse and only during the moments of totality when the sun's disk is completely covered by the moon. In that case, you're only viewing the corona and it's about as bright as the full moon. But you want to make sure that if you are viewing the corona with your own eyes, which I highly recommend that you do because it's really beautiful, if you view it with your eclipse glasses on, you won't see the corona at all. Be careful that you put your eclipse glasses back on before totality ends. It's extra dangerous to see the sun, more dangerous than usual to look at the sun, the surface of the sun, after totality ends because your eyes have dilated. Because it's so dark during totality, your pupils get larger so you can take in more light, and so you can damage your eyes even more if you're looking at the sun after totality ends. So what I plan on doing is when totality starts, I'm going to take off my eclipse glasses. I'm going to set a timer based on what that NASA map tells me is the duration of totality for that location. And I'm going to make sure I give myself enough time to put my eclipse glasses back on.
Great. Roger on LinkedIn asks, can the astronauts and cosmonauts on the International Space Station see the eclipse?
That's a cool question. Yeah, so they will be able to see, kind of like what Jason was just showing us, they'll see that same simulation, but they'll be seeing it for real. So they'll be able to see the shadow of the moon pass over the Earth in a really cool way. And they'll be able to distinguish between the penumbral shadow and the umbral shadow. So I actually would prefer to view the eclipse from the ground. So I can see, I can experience nighttime during the day and see that corona. But I bet the view from the International Space Station is also really cool.
Great. Miles on YouTube asks, will the sky darken at 80% path for the 2023 eclipse?
Yes, yeah. So the sky will get dark even if you aren't in the path of totality. So if you're seeing a partial solar eclipse and 80% of the solar disk is covered, it will get darker, but it won't get as dark as if you were viewing totality. For example, that last 1% cover of the surface of the sun corresponds to experiencing it getting darker by a factor of 10,000. So the more of the sun that gets covered by the moon, the better in terms of your experience of darkness.
Cool. Let's see. TNL Carson on Facebook asks, is Eyes on the Solar System available for download because they sometimes present in rural areas with no broadband access? Jason, I think that question's for you.
That is an excellent question. So to open up Eyes to mobile phones and tablets, to expand the reach of it, it's difficult to have it offline. We are working on offline versions that would be a download, but they are not ready yet. We used to have a video game that we have now gone off of because anyone with a mobile phone couldn't use it. So that is coming, but it is not available right now.
Emma Becht on YouTube is asking, are there any planets that have a constant eclipse? Is that even possible? And greetings from San Diego.
Oh, that's an interesting question. So I don't know off the top of my head. I suggest that you use NASA Eyes, like Jason was showing, and simulate some scenarios in the solar system. That sounds like a cool experiment to do.
Yeah, I would say go to our Eyes on Exoplanets because some of those exoplanet systems are really crazy, very packed and dense. So you go explore some of those.
Yeah, there are some exoplanets that transit in front of their star like as often as every 3 days as seen from Earth. And with a small telescope, you can actually see it yourself, which is one of the projects I work on, Eyes on Exoplanet Watch. It will let you use a backyard telescope and look at planets transiting in front of their stars in other solar systems. So that's pretty cool. Sandika on LinkedIn asks, will Asian countries be able to see the eclipse? And I guess a more extrapolated question is, if you can't see the eclipse in person because it's cloudy where you are, or because you're in another part of the world that won't be able to see the eclipse, is it going to be broadband, like live streamed anywhere?
Yeah, that's a great question. So yes, if you can't view these particular solar eclipses because you aren't in North America or Central or South America, then there's lots of ways to view the eclipses online. It will be live streamed somewhere. I can promise you that. NASA's going to live stream it Many other universities are going to live stream it. So if you can't experience the eclipse in person, I highly recommend that you go online and experience it that way. And you probably don't have to wait too long until there is a total solar eclipse passing somewhere in your approximate geographic region, much closer than North America, at least.
Cool. And Tia and L. Carson have another question. They're also on Facebook. Can you follow the path of totality? Is there a miles per hour speed of the shadow such that you could drive along a highway and like follow along and see a longer totality?
I like where you're going with that question. That's a good one. If you can fly at 1.5 Mach speed, then yes. But I don't know how to do that. So unfortunately, no. The shadow travels at a rate of thousands of miles per hour. So you can't follow it in a car. You just have to know in advance, just like Jason did, that you're going to have to chase the eclipse in Missouri well enough in advance that you have time to drive there.
That's some great advice. And we are running out of time. So Rachel, we've got time for one final question for Marin and Jason.
One more question. There was a really good question here. Let me see if I can find it. Vibe Have on LinkedIn asks, it's incredible to see you with so much depth of knowledge. Can you tell us something about you? Were you always excited to explore the solar system?
Oh, what a cool question. Yeah, I think I was. When I was a kid, I had a lot of books about astronomy. I think I just liked looking at pictures of space, and it made me so curious. I actually didn't think about astronomy as a career. I didn't know it could be a career path until I was in college. I liked physics in high school. I thought I was going to major in physics in undergraduate school. And it wasn't until I got to University of California, Berkeley, which is where I got my undergraduate degree, that I realized that astronomy could be a career path. And I haven't looked back since.
And Jason, how about you?
Yeah, I also, my undergrad is astrophysics as well. I didn't get a PhD. I went into software development. And I grew up in Kansas, so I had a lot of clear skies and lots of stars. So that probably prompted a lot of that. So I feel fortunate to be here. And you can really, you stay at JPL, NASA for a while, the knowledge will start piling up. So it's a great place to be.
So folks, we are so grateful for the time you spent with us this evening. Just a couple reminders. If you are going to view the eclipse, make sure you do it with safety glasses or other tools. There's some great resources online. If we can pull up images 20 and 21, JPL's Education Office and NASA Resources Office have some amazing tools for you. And the homepage for this is going to show up on the bottom screen here, solarsystem.nasa.gov/eclipses. I want to thank our guests this evening, Dr. Marin Anderson and Jason Craig, for joining us to discuss the incredible eclipses coming up. Also, thank you to our wonderful questions co-host Rachel Zimmerman-Brockman and everyone working behind the scenes to make all of this possible. And especially to you watching this evening or at any time, thank you for taking the time to join us every single month. If you've missed one or would like to revisit any of our Von Karman series from the past 5 years, they are available on JPL's YouTube page. Remember, don't look directly at the eclipse without proper safety glasses, but do join us next month for a discussion on the Europa Clipper mission. Thanks again, and we'll see you in October. Bye, everyone.